Welcome. We are going to do a little bit of review of alcohols. Why don't you join me on page 119 of your workbook? And in this video, what we'll plan to do is a review of classifying alcohols as primary, secondary, or tertiary, the IUPAC naming of alcohols, and the two reactions of alcohols that we have looked at, dehydration and oxidation. So for classifying alcohols, one page prior, 118 has some practice problems on classifying alcohols. Let's take a look at a couple of those. Remember that what makes something identify as an alcohol is OH bonded to carbon, 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 and OH bonded to carbon. Once you see that something is an alcohol, to determine if it's primary, secondary, or tertiary, what you want to do is look at the alcohol group, which I've highlighted in yellow. Look at that group and count how many bonds to carbon are attached to the group. That yellow alcohol group is bonded, making one bond to carbon, so this is a primary alcohol. The one below it, I see that that yellow alcohol group is making 3 bonds to carbon, which makes it a tertiary alcohol. The one below it is making 1 bond to carbon, so it is a primary alcohol. The fourth one is making 1 bond to carbon, and so it also is a primary alcohol. Number 5 is making 2 bonds to carbon, so it is a secondary alcohol. And finally, number 6 is making 2 bonds to carbon, so it is a secondary alcohol. So again, first identify the alcohol functional group itself, and then count how many bonds to carbon are attached to that alcohol functional group. That is a review of classifying alcohols. The next thing for us to review is naming alcohols, the IUPAC system of naming. I'm going to flip the paper over for that. On page 120 of your workbook, I've listed some common alcohols in health and the human body. And on the bottom of that same page, I've listed several alcohols that we'll use to practice naming. What you'll want to do always is identify the alcohol group itself, OH bonded to a carbon, and then find the longest continuous chain that includes that alcohol functional group. In this case, it's that longest continuous chain. And then the next step is to number the carbons in that longest continuous chain, and you will number them sometimes from the left end, sometimes from the right end. The way that you know which end to start with is number from the end closest to the alcohol functional group. So I'll number from this end, closest to that alcohol functional group. 5 carbons, that's pent. The alcohol group is attached at carbon 2, and that's why it is 2-pentanol. The OL tells us that it's an alcohol. The pent tells us that there are 5 carbons in the parent chain. Remember, the parent chain is the longest continuous chain of carbons. And then the 2 tells us that the OH is attached to carbon 2. The next one, again, start by identifying the alcohol functional group. Highlight the longest continuous chain that includes that alcohol group. Number closest to the alcohol functional group. And in this case, I see that we have 2 additional carbon, each as a separate methyl group, 2 groups attached to that chain. So I've boxed those out in blue just to make sure that we notice them. The naming will look like this. The longest continuous chain is 5, so it's a pentanol. The OH is attached at carbon 1. I see that I have a methyl group here, and it's attached at carbon 2. And I see another methyl group. It's also attached at carbon 2. So that is named as 2,2, I'll just write it again, 2,2-dimethyl-1-pentanol. The ol tells us it's an alcohol. The pent tells us there are 5 carbons in the longest continuous chain. The 1 tells us that the alcohol is attached at carbon 1. Dimethyl tells us that there are 2 separate methyl groups attached, there and there. And then the numbers 2 and 2 are telling us where each of those methyl groups are attached. Let's jump down and do 1 or 2 of these bottom examples. I'll do this one. There's the alcohol functional group. Here's the longest continuous chain that includes that functional group. We will number closest to the alcohol group, and I can see that there's something attached. It's a methyl group attached. The longest continuous chain is 3, so that's prop. It's an alcohol, so I'll call it propanol. The alcohol group is attached at carbon 1, so it's a 1-propanol. And then we see that we have a methyl group at carbon 2. So 2-methyl, 1-propanol. When you have the line angle notation, that doesn't change anything. Highlight the alcohol, highlight the longest continuous chain that includes that alcohol, number closest to the alcohol group. Remember, it's an oxygen, so this is a carbon, 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 and carbon. There's nothing attached, so I would say this will be a hexanol. Hex because there are 6 carbons in the longest continuous chain. All because it's an alcohol, and the OH group is attached at carbon 1, so this is 1-hexanol. I guess I might as well do these last couple. This is cyclo because it is a cyclic compound. It's a hex because there are 6 carbons, and the OL tells us it's alcohol. So this is cyclohexanol. You won't be naming cyclic compounds that have 2 different things attached. Alcohol is attached. You won't name it if there is another group attached. So this is cyclohexanol. The bottom one is an alcohol. We see that here. The longest continuous chain of carbons that includes that alcohol is 4. That's what I've just highlighted. I see we have a methyl group attached, and we will number closest to the alcohol group, which I have just done. So we would name this as 2-methyl 2-butanol. All because it's an alcohol, but because the longest chain contains 4. The 2 in front of butanol tells us that the alcohol is on carbon 2. 2-methyl tells us that there's a methyl group attached on carbon 2. So those are our examples of IUPAC naming of alcohols. The last thing that we'll review in this video is reactions of alcohols, specifically the dehydration reaction that we've looked at, and then the oxidation reaction. So join me, please, on page 121, and we'll take a look at first the dehydration reaction. Dehydration is the reverse of hydration of alkenes. So I'm going to write a general alkene. This is what we saw first. We saw that if you hydrate an alkene, The double bond turns into a single bond. The double bond has turned into a single bond. One carbon gets an H, one carbon gets an OH. That's what hydration looks like. The reverse reaction then will be dehydration. So if you hydrate an alkene, the product is an alcohol, which means in reverse, if you dehydrate an alcohol, the product is an alkene. You can hydrate an alkene. You cannot dehydrate an alkene. There isn't any water to remove. You can dehydrate an alcohol, but you cannot hydrate an alcohol. So hydration happens to alkenes, dehydration happens to alcohols, and that's what we'll look at here. Here's a general example. This, of course, is an alcohol, which means it can be dehydrated. The reactant, or the other reactant catalyst, I will say, that's used in this reaction is concentrated H2SO4. When you see that, that's an indication that it's a dehydration reaction. Sometimes you'll see the triangle, which is a symbol for heat, but when you see concentrated H2SO4, that will mean it's a dehydration. So I'll write this, I'll say, aha, that means dehydration. And when you dehydrate, it's the opposite of hydration. We are removing water. So remove H, remove OH, which means definitely that H and that OH make water. Definitely water will be a product. What happens to the rest of the alcohol compound? The bond that used to be a single bond becomes a double bond. That bond to the H has been broken. This bond to the OH has been broken, and so those a new bond forms between those two carbons. So let's look at a couple of examples of that. Here is an alcohol. I see the OH on a carbon. This is my indication that it will be dehydration. I see H2SO4 and I see the symbol for heat. So what will happen is the carbon skeleton will not change. In fact, I'm going to write the carbon skeleton. Looks like that. It will not change, but we will be removing an OH and we'll be removing an H. And in the process of doing that, we'll form a double bond. The OH is here. The OH is the OH of the alcohol. The H needs to be on an adjacent carbon. That means a next door neighbor carbon. So not these H's here. It needs to be on an adjacent carbon, which means it needs to be this one. These H's are on a carbon, 2 carbons away. Same here. So this is the H that will be removed to make water. Tells me that I know for sure our other product will be water. That OH and that H becomes this water. And then the double bond will form between the 2 carbons that had the OH and the H. So this carbon gave the OH, this carbon gave the H. And so the double bond will form here. This is now an alkene. It's no longer an alcohol. Now it's an alkene. We didn't have a choice of where to put that double bond. There's only one place because there's only one carbon adjacent that can give us the hydrogen to form the double bond. Let's take a look now at this second example. I see that this is an alcohol. Here's our sulfuric acid and heat. That tells me that this will be a dehydration. Now I take a look at what will get removed to form water. OH will be from the alcohol. The hydrogen will come from an adjacent carbon. I see now that there are a couple of choices. I could remove one of these hydrogens. This carbon is adjacent. I could remove one of these hydrogens. This carbon is adjacent. Or I could remove this hydrogen because this one is adjacent. each of those will give us a different product. Let's take a look at what those three options would look like. I'm going to draw it this way. If I remove this H right here, remember that the carbon skeleton in all cases does not change. So here was our carbon skeleton. I could even write now, I could write it for all three. The carbon skeleton is the same. I think I missed a carbon somewhere. Yeah. So the carbon skeleton doesn't change. What does change is where will the double bond go? It's going to connect this carbon here, which is here, either to this carbon, or to this carbon, depending on which hydrogen gets removed. If we, in the first case, allow this hydrogen to get removed, then the double bond would go here. If we allow this hydrogen to get removed, then the double bond would go here. And if we allow this hydrogen to be removed, then the double bond will go here. So I'm gonna write in words, or write down what I've just drawn. There are three possible dehydration products. Those are the three that we've just shown. Depending on which hydrogen you remove, the double bond will be in a different place. The major product is determined by Markovnikov's rule. I'm sorry, Zaitsev's rule. And Zaitsev's rule says that the major product will be the product where the alkene, the double bond, is most substituted. And by most substitute, has the most bonds to carbon. So let's take a look. And I think what I'll do, just to emphasize it, is draw a little box around the alkene. And our question is, which of those alkenes has the most bonds to carbon? This one has 3 bonds to carbon. This one has 2 bonds to carbon. This one has 4 bonds to carbon. And so this one will be, the major product. Notice this does not always come into play. The first example we gave, there was only one possible product, and so that's the predicted product. If, however, you have a situation where there's more than one choice of where to draw the alkene, where to put the alkene in your product, we actually had 3 possible products that we could have formed. When you have a case like that, where there are 2 or more possible products, the predicted product, the major product, will be the product where with the alkene that's most substituted, has the most bonds to oxygen, most bonds to carbon, sorry. That is called the Zaitsev's rule. I'm going to flip our paper back to our overview page. We have now reviewed classifying alcohols, we've reviewed naming, and we just now reviewed dehydration. The last reaction that I'd like to review with you is oxidation. And to do that one, I will have us flip the paper over from dehydration. So on page 122, you will see at the top of the page, oxidation and reduction of alcohols. So when we're looking at oxidation of alcohols, remember that oxidation will involve making more bonds to oxygen. As you know, carbon makes a total of 4 bonds. So if it's possible to make more bonds to oxygen, that's oxidation. In the process, something would need to be removed from the carbon, and that would be hydrogen. So we have drawn this a couple of times. We've said oxidation means gaining oxygen or losing H. The opposite of that is reduction, which would be losing oxygen or gaining H. The reason I'm reminding you of this is because when we go through these structures, in order to be able to make an additional bond to oxygen, you'd have to kick out a bond to something, and that something is H. So if we want to oxidize, for example, this alcohol here, and I'm going to draw I'm going to indicate oxidation just by writing that symbol OX. Sometimes the oxidation will be indicated by showing the formula of an oxidizing agent. Sometimes it'll be just a OX abbreviation to indicate oxidation. You can see that this is an alcohol, and you can see that it's a primary alcohol. What happens if we try to oxidize a primary alcohol? The first step that I recommend you do is to draw the alcohol. Just copy it over with no H's shown. So leave the hydrogens off for the moment and draw just the carbons and oxygens. So I've done that here. As you know, it doesn't matter if you draw it. Here the oxygen is pointed sideways, here it's pointing up. That doesn't change the bonding. So draw the structure with no hydrogens showing. Look at the carbon that already has a bond to oxygen. That's where you start. You won't start with a carbon that has 0 bonds to oxygen. Look at the carbon that already has a bond to oxygen and ask yourself, is there room on that carbon for any more bonds to oxygen? Keeping in mind that carbon makes 4 bonds. And since I see only 2 bonds shown, I would say, yes, I can make another bond to oxygen. So I'll do that. That would look like this. I just oxidized this by making an additional bond to oxygen. And then we'll ask ourselves, can it continue to be oxidized? It's still sitting in the test tube with the oxidizing agent. Can oxidation of this structure happen? Our question we answer in the same way. Look at the structure with no hydrogens shown. Look at the carbon that has oxygen bonded to it already and ask yourself, is there room on that carbon for more bonds to O? 1, 2, 3. Yes, there's room for 1 more. And so 1 more bond would look like this. You know that oxygen cannot make a triple bond, so we cannot put a triple bond there. We have to start a new bond. So 3 bonds to oxygen always looks like this. We could ask ourselves, could we continue to oxidize that? But if you notice, the carbon that has bonds to O already is using up all 4 of its bonds. 1, 2, 3, 4. It's using all of them. There's no way to add any more. So that would be no reaction. This structure here cannot get oxidized, no reaction. When you are at this point where you realize that no more oxidation can occur, that's where you want to go back and put the hydrogens back in, redraw the hydrogens back in the structure to make it a little bit easier to identify the functional groups. Specifically, remind yourself that oxygen makes 2 bonds, carbon makes 4 bonds. So if a bond is not shown, you know that it's a hydrogen. This oxygen already is showing its 2 bonds. It does not get a hydrogen. This oxygen is only showing 1 bond, so the other bond must be a H. This carbon is showing all 4 of its bonds. It does not get an H. We could draw the H's in on this carbon. I'm not going to though. I'm putting the H's in only to be able to finish the functional group and identify the functional group. I see that this is carboxylic acid. Over here, oxygen does not get a hydrogen. It already is showing its 2 bonds, but carbon is showing only 3 bonds, 1, 2, 3. So if I want to identify what is this structure, I see that that carbon needs one more bond, which would be hydrogen, and this helps me see this is an aldehyde. Please notice though, I waited until we were done with figuring out the oxidation part. We waited till we were done with that to go back up and put in the hydrogens again. Leave them out when you're doing the oxidation to help you figure out what the oxidation products are more easily. This one here is a secondary alcohol. Can a secondary alcohol get oxidized? Here's how we'll answer that. We'll say this. We'll say, I don't know. Let's figure it out. Let's figure it out by drawing it out. So can oxidation happen? I don't know. Let's find out. Copy it with no H's showing. So I copied the carbon skeleton. I left the oxygens in, but no H's. That was the first step. The second step is to look at the carbon that already is making a bond to oxygen and see if there's room on that carbon for more bonds to O. This carbon has 1, 2, 3 bonds showing, so yes, there is room to make one more bond to oxygen. Could that keep going? Could that continue to get oxidized? That carbon is showing 1, 2, 3, 4 bonds to O, so no, it cannot continue to get oxidized. For this to try to be oxidized would be no reaction. Then we would go add hydrogens where they belong. Oxygen should have 2 hydrogens showing, and it does, or 2 bonds showing, and it does. Carbon should have 4 bonds showing, and it does. So we don't draw any hydrogens for this structure. We can identify it already as a ketone. Finally, this last alcohol is a tertiary alcohol. What happens if we try to oxidize a tertiary alcohol? You can see from the original structure that that carbon is already, you can see from its original structure that this carbon is already showing all 4 of its bonds. Carbon, 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 oxygen. It's not using any of its bonds to hydrogen. It's already using them for carbons and oxygens, which means that it cannot be oxidized. Tertiary alcohols cannot be oxidized because there's no available bonds to add bonds to oxygen. Let's take a look at a couple of examples down below. Notice here it shows the formula for sodium dichromate. You recognize that as an oxidizing agent. You worked with that, saw that in the lab. That tells you that it will be an oxidation reaction. What we'll do is what we did above, draw that structure with no carbons or with no hydrogen showing. So the carbon skeleton looks like this. Draw the carbons, draw the oxygens, but not any hydrogens. Look at the carbon that already has an oxygen attached, which is this one here. Ask yourself if there's room on that carbon for any more bonds to hydrogen. Right now it's showing 1, 2, 3 bonds, so it has room for one more. So I'll draw in the one more. I can't keep going though, right? This carbon already now has 4 bonds, which means we're done. That cannot get oxidized anymore. So the final product is this. This was a secondary alcohol. And when it gets oxidized, what we've produced is a ketone. That's not something that we identify by memorizing. That's something that we identify by drawing it out and figuring it out. This one, I see this as a primary alcohol. If I want to know if it can be oxidized, again, this is an oxidizing agent, so this will be oxidation. If I want to know if this can be oxidized, I'll draw that structure with no carbons, no hydrogen shown. So there's 1, 2, 3, 4 carbons. The last one has an oxygen. Is there room on this carbon for another bond to oxygen? Yes, there is. Is there room on that carbon for another bond? And you can do it in 2 steps if you like, or 1 step. The final product will be the same. So first we added 1 bond to oxygen, and then we ask, is there room to add another bond to oxygen? Yes, there is. Is there room to add yet another? That answer is no, because this carbon already has 4 bonds to oxygen showing. So at that point, you can go draw in the H's to finish out the functional group. I've drawn it a little bit on purpose, not in the regular way that we would draw a carboxylic acid or the way that we would draw an aldehyde, but that's to remind you whether the H points down or up, double bond points to the side or up or down, doesn't change what the functional group is. This is aldehyde, this is carboxylic acid. So if you oxidize at primary alcohol, your final product is carboxylic acid. Last example here, this is an alcohol. This is a tertiary alcohol. If you need a reminder of that, carbon with an OH is the functional group, and it's making 3 bonds to carbons. So this is a tertiary alcohol, which means that there will be no reaction. This is no reaction because that carbon right there, the carbon that's bonded to an O, has no available bonds to use. It's already using up all 4 of its bonds. So oxidation of alcohols, if I ask you, can an alcohol get oxidized? You need more information. It depends what kind of alcohol. Primary alcohols can get oxidized. They form an aldehyde, which keeps going to make a carboxylic acid. Secondary alcohols can be oxidized to form a ketone. Tertiary alcohols cannot. In our next video, we'll look at oxidation reactions of aldehydes and ketones, but you actually already know about that from what we've just done. Aldehydes, yes, can get oxidized to form a carboxylic acid. Ketones are a no, they cannot get oxidized. We'll look at that in the next video, and we'll look at a little bit of naming as well. What we've just finished with in this video is the last part of alcohols, oxidation of alcohols. Thanks for joining.